Welcome, 12th graders, as we continue our look into applications of derivatives, looking at ways to apply the calculus that you've been learning. In section 7.6, what we're going to start doing is we're going to start looking at the relationship between the first derivative, the second derivative, and the graph of a function. And we're going to go a little bit beyond just the slope of a tangent line and normal line that you're used to using at this point. Okay? Now, I want to highlight the three learning goals, and this is going to be made up into either 2 or 3 videos, we'll see, so that they're all reasonable length, hopefully. The first thing that I'm going to want you to do is to learn to use the first derivative to determine intervals on which a function is increasing or decreasing. We're about to do that. The second thing you're going to be able to do is, again, use the first derivative to determine where the relative extrema of a function are. And by relative extrema, I mean relative minimum values and relative maximum values. Might seem a little weird right now, but that's a pretty easy concept. You'll understand it pretty well. And then the third thing we're going to do is we're going to learn how you use the second derivative to find what are called inflection points and to determine the concavity of the function of a graph on specific intervals. Whether or not the graph is concave up or concave down at certain points is what we're going to be looking at. Okay, so let's go on to look at how you use the first derivative to determine the intervals for which a function is increasing or decreasing. Alright, we're going to come back to the example that you see on your screen here in a moment. I want to explain the whole concept of increasing and decreasing intervals first, and I'm going to show you a graph in order to do that. Now you see the graph of this function, and if you look over on the left-hand side of my GeoGebra window, you're going to see the equation of the graph. This is the function f of x equals negative 1/2 x to the 6th power minus x to the 5th power plus 9x squared minus 3. And what we're trying to do, again, is we're trying to learn how to determine the intervals over which a function is increasing and decreasing. Now, I want to make sure I preface this. Ultimately, what you ought to be able to do is use calculus to make the graph of a function without the aid of a calculator. Alright? That's one of the things in an AP calculus class that you would do. We're looking at the graph, and so it seems fairly obvious where the function is increasing or decreasing, but the principles we're going to learn are going to help you know whether a function is increasing or decreasing, even if you're not looking at the graph. Okay? But let's go ahead and look here. A function is increasing on a certain interval simply if y is increasing as x is increasing. And so you see that interval that I just highlighted, the value of y is getting larger as the value of x is getting larger. Here's another interval on which the function is increasing. Y is getting larger as x is getting larger. And a function would be decreasing on an interval if the value of y is decreasing as x increases. Here's a decreasing interval. You see y is getting smaller as x gets bigger. And here's another decreasing interval. Alright, just going to label that. The reds are decreasing, and the green is increasing. Alright, I already told you that our goal is to be able to just kind of look at the equation of a function as you see in the left-hand side, and to be able to use that function in order to determine where the graph is increasing or decreasing. And you might have a good idea of how we might be able to use the first derivative to do that. Because isn't it the case that whenever you're looking at an increasing interval, that if you were to draw the tangent line of a function at any point on that increasing interval, that tangent would have a positive slope? Or in other words, on increasing intervals, the first derivative is positive. F prime of x is greater than 0 on an increasing interval. And here again, f prime of x is greater than 0. Whereas, if you're looking on a decreasing interval, the slope of the tangent line is negative, or in other words, f prime of x is less than 0 anytime the interval on a graph is decreasing. Okay, so already I think you understand the concept of how you determine whether a function is increasing or decreasing with the first derivative. All right, find where the first derivative is positive and where the first derivative is negative. Now there's a little bit more that I want to discuss with you, and this is going to help you to actually learn how you determine where the first derivative is increasing or decreasing. Let me erase all this stuff that's on the screen. If you wanted to just know from an equation where to look to see if the derivative is increasing or decreasing, it's kind of hard to know where to start. Now looking at the graph it seems fairly obvious, but looking at the equation it doesn't look so obvious. Well, let's use the graph to aid us here. You're going to notice the spots where the function switches from increasing to decreasing and vice versa are all maximum or minimum values, or what's called a relative maximum value, such as that right there, or a relative minimum value, such as that one right there. Here's another relative maximum value. And of course, at any of those points, you have a horizontal tangent line, and you can determine where those points are then by setting the first derivative equal to 0. And any point on the graph where the first derivative is equal to 0 is what's called a stationary point on the graph. And if you're trying to determine when a function is increasing or decreasing, you've got to know where those stationary points are. Now, I'm going to show you something you could do with your graphing calculator on a paper where you're allowed to use your graphing calculator. You know how to use the power rule to find the derivative of that function, and you might even recognize that this equation that I have right here in g of x actually is the derivative of function f of x. So what I want to do right now is show you how you can use the first derivative to find out where these stationary points are that you use to determine where the graph is increasing or decreasing. Alright, let's go ahead and look at the graph of that first derivative of the function. And what I want you to pay attention to is where the first derivative is equal to 0. Okay, because we said that's where the stationary points are that separate increasing and decreasing intervals from one another. Alright, now using my graphing software, here's what I'm going to do. I'm going to follow the graph of the first derivative, which is in red right here, and I'm just going to try to figure out where is the x-intercept for each of those, because the x-intercept is where the first derivative that is equal to 0, if I'm looking at the graph of the first derivative. And you can see over at the left-hand side of the screen how it says the coordinates of those points A, B, and C that I just made. Alright, now the next thing that I'm going to do is I'm going to make vertical lines that go through each of those points. I'm going to make the vertical line x equals negative 2.22. I'm going to make the vertical line x equals 0, which is the y-axis, so you're not really going to see it. And then I'm going to make the vertical line x equals 1.27. So I used the first derivative to find out, I looked at the graph of the first derivative to find out where the first derivative is 0, and that shows me the places, the stationary points that separate the increasing from the decreasing intervals. Let me turn off the graph of the first derivative real quick, and then I'm going to write something on the screen. Okay, those 3 vertical lines that I made divide this graph into 4 intervals. And on those 4 intervals, the function is either increasing or decreasing. Now, if you look at the first interval to the far left, here's an increasing interval. And we could say that that interval goes from negative infinity to negative 2.22. It doesn't include negative 2.22 because at that point the function is stationary, meaning it's not increasing or decreasing because the first derivative is 0. It's a horizontal tangent line. The second interval where the function is increasing or decreasing occurs from there to there, which happens to go from 0 to 1.27. All right, so two increasing intervals. I'm going to change colors here for the decreasing. All right, now we had two decreasing intervals as well. You can see the interval from negative 2.22, there should be a decimal point there, to 0 is an interval where the function is decreasing. And then the interval from 1.27 up to infinity is the next interval. Great. I hope at this point you have an understanding of what increasing and decreasing intervals are. I would like to work an example from your textbook to show you how you can just look at the equation and make those determinations. So let's do that. What I'm looking at here is example 22 from chapter 7, and what it's asking you to do is to use the derivative of f to find the intervals on which f is increasing or decreasing. Now there's three examples here. For the sake of time, I'm going to work example B alone with you, but the same principles that I apply here, you could apply to the function in either part A or part C as well. Now I want to have a side note right here. We were talking about in the last example where we looked at the graph of a function about what a stationary point is, and here's where the textbook tells you what a stationary point is. It's where the first derivative is equal to 0. But truly what you want to do is you want to look for all the critical numbers on a graph when you're trying to determine where the graph can switch from increasing to decreasing and everything. Now a stationary point is a critical number, but also a critical number includes places where the first derivative is equal to 0 or the first derivative is undefined. And in particular, when you're thinking about where the first derivative is undefined, what you're thinking about are vertical asymptotes. Okay, now I'm going to change the screen here so that I've got a little bit more room to work. Our first goal here in finding out where this function is increasing and decreasing is to find any critical numbers, including stationary points and places where the function is undefined. Where the derivative is undefined. Okay, so let's go ahead about that. We've got to find the derivative to do that. Now we have found so many derivatives at this point, it's going to waste our time in the video if I show you the work behind the derivative. I'm going to go ahead and show you what the derivative is. You know how to use the quotient rule to get this. The derivative of this function is f prime of x is equal to 6x over x squared minus 1 squared. Okay, we've got to do two things right now to find critical numbers. All right, critical numbers. And the first thing I'm going to do is I'm going to find out where is the first derivative equal to 0. And so I'm going to set 6x over x squared minus 1 squared equal to 0. Let me come up here where I got a little bit more room to work. And in order to find out where that equation is equal to 0, I'm going to multiply both sides by the denominator. I'm going to get 6x equals 0. And so x equals 0. All right. The first derivative equals 0 when x is equal to 0 for this particular function. Also, there are a couple of vertical asymptotes here. If you look at the denominator, there are two values of x for which the function would be undefined. And let me go ahead and label those. All right, we're going to have a vertical asymptote at x equals positive 1 and at x equals negative 1. So our three critical numbers are x equals 0, x equals 1, and x equals negative 1. And what we need to do is look at all the intervals that lie between each of those critical numbers, and to the left of all of them, and to the right of all of them. It's going to be 4 intervals in all. Let's go ahead and continue this. Now please, if you haven't done it already, because I forgot to mention this, don't look at the graph of the function yet to determine the increasing and decreasing intervals, because it's going to be kind of cool to see how you figure those out without ever looking at the graph. And then you check the graph later, of course, to see that you were right. What you're going to notice is that I just labeled those 3 critical numbers on a number line. And what I'm going to do right now is I'm going to look at the intervals created by those critical numbers. And those intervals are these. We're going to look at the interval from negative infinity to negative 1. We're going to look at the interval from negative 1 to 0. Now notice these are all in parentheses. These critical numbers are not included in these intervals. 0 to 1 is the third interval, and 1 to infinity is the fourth interval. And simply what I want to do is I want to determine what is the sign of the first derivative at each of those values. So have your calculators handy. You already know what the first derivative's equation is. We know it was f prime of x equals 6x over x squared minus 1 squared. What I'd like you to do is this. I'd like you to pick one number in each of those intervals, just some representative number. And let's say between negative infinity and negative 1 that you choose negative 2. Between negative 1 and 0, why not negative 1/2? And then choose positive 1/2 between 0 and 1, and then choose 2 between 1 and infinity. And I want you to find out what the sign of f prime of each of those things is. Alright, go ahead and take a moment and do that. Now, I've just written a lot of things on the screen. You can see that for both the negative values that we plugged into the first derivative, that the first derivative was indeed negative. Alright, just coincidental, but that is the way that that worked out. And then you can see that for both the positive values that we plugged into the first derivative happened to be positive. And so we have 2 consecutive intervals where the function is decreasing, and then 2 consecutive intervals where the function is increasing. Now, how in the world can you have 2 intervals where it's decreasing? Here's the other thing that I wrote. Remember that negative 1 was a vertical asymptote, and the graph on the left-hand side of a vertical asymptote and immediately on the right-hand side of the vertical asymptote aren't connected. So they can both be decreasing, and it's not really a weird thing. Now, that's the same thing for the other vertical asymptote over here. To the right side of x equals 1 and to the left side of x equals 1 is not really weird that both were increasing, because they can do anything on either side of that vertical asymptote. Alright? Now, when we were looking at 0, the critical number where the first derivative was equal to 0, it was possible that we had something where the graph went from decreasing and then decreased again on the other side, or it could have gone from decreasing to increasing. There are lots of choices right here. Alright? But the point is this. The increasing intervals, I'm going to highlight those in blue, were from negative infinity to negative 1 and negative 1 to 0. And the decreasing intervals, which I'm going to highlight in this orange color, were the intervals 0 to 1 and 1 to infinity. Now let's look at the graph and see that that worked out, and then we'll be done with this video. Now this is the graph of the function f of x that we're looking at. You can see the equation in the window on the left again. Exactly what we're looking at. And I went ahead and graphed the 2 vertical asymptotes as well. You can see the red lines right there. And indeed, what we just said is true. On the interval from negative infinity to negative 1, the function is decreasing. And then it happened that just on the other side of that vertical asymptote, on the interval from -1 to 0, the function was decreasing as well. Now, right here, where x is equal to 0, you see the horizontal tangent line. The function was neither increasing or decreasing. It was stationary at that point. And then on the other side of that, it turned out the graph switched from decreasing to increasing. And on the other side of the vertical asymptote, on the interval from 1 to infinity, you can see that the function was increasing. Alright, that's pretty cool analysis for a graph. We were able to do a pretty good job of creating that graph without even looking at the graph to begin with. Very nice. We've got a couple more videos that we're going to watch from this section ultimately. Hope you learned a lot. I'll see you in the next one.